Okay, we'll have to continue this without my video, otherwise I can't. Okay, it doesn't seem that I can't write notes on the slides, and that will be harder without the notes for me to explain the concepts. So, bias-variance trade-off revisited. Let's see. We have seen it before as a means of bandwidth selection for kernel density estimation in lecture 11. The task was to pick the kernel width that is optimal to minimize the error between the estimated density and the true density. So for that, and I'm just repeating the slide from before, for that we agreed to use the mean squared error. Interesting. Let's try to erase this. So the mean squared error is nothing this a difference between our estimate and the true density squared, and we want to minimize that distance, even though we don't know the true density in this case. But the point was to show that if we open up the square, we'll get that. If you want to use that, I'm doing nothing but taking advantage of this good old formula that you can derive for yourself. Well, in this case, it's a minus b to ab plus b squared. By multiplying through, you can get it yourself. So, well, but what do we do with this? Expectation is linear, so we can just take it inside or open it up, which we do here. An expectation of something that doesn't change because the true density stays the same. It's just a constant or the quantity by itself. And then we do the trick. We add and subtract square of the expectation of our estimator. Add this part and subtract this part. But after we've done that, we've completed the square here, and we get two quantities, which back then I said are example of a bias-variance trade-off. This is just the bias, well, it's actually bias squared, because this is the expectation of our estimate minus the true value. So we will converge in the limit of the data points to this quantity. And if we are unbiased, if our estimator is unbiased, we will practically converge to this same quantity on the right here, and the difference will be 0. But it doesn't have to be 0, right? Our estimator may as well be biased. And this is variance. Let's see on the next slide what is bias and what is variance. This is just an illustration of how we can think about it. In here, in this target, we see that we have low bias. That means, well, we're not right on target, but we're pretty close to it. And we have low variance. The spread of our shots of our points is not too high. When we have low bias, we're still, our center of mass or our mean is somewhere close to the target, but we have higher variance, the spread of these points. And then we have high bias, right? That is, we're way off. But low variance, we can have them separately. We can have, as you see here, high bias, quite a difference between where we want to be and where we are, but still we're pretty sure. If you use, sometimes variance is used as a measure of certainty. If our model is very certain, low variance, that doesn't mean it's correct. That's one point. Another point, we can have both. We can be highly incorrect, that is, have high bias, and highly uncertain, that is, high variance. So let's see a specific example. Bias-Variance Decomposition for mean squared error. So theta hat here is our estimate of the parameters, and theta are our true parameters. This is nothing but the mean squared error expectation of this difference with respect to the data. Let's do the same as before. We opened up the square, we completed the square to, we opened up the square. The expectation as a linear quantity operator went inside. Since this parameter, the true parameter, is a constant or a value, not a random variable, expectation of this with respect to data is the same, so there is no expectation here, but expectation of our estimate with respect to data still, we need to compute it, right? This is nothing but our mean, or the center of mass of our expectations of parameter estimates for each of the data points. We use the same trick as before. We add and subtract square of the expectation of our parameter estimate. Then we'll get this quantity, which is completed square as before. This is bias squared, and this is variance. But wait, isn't variance the difference between our the square of the difference between our estimate and the mean of our estimate, right? How did we get there? So let's start with more classic expectation of, that's what's written there practically, right? That's what you're used to seeing. Let's start with it, and we open up the square here, clear, no magic, and then we take the expectation, and using linearity property, we obtain this expression. So what happened here, again, remember, after we compute this expectation, it will be just a number. It is the same under this distribution, and so computing that expectation twice doesn't change anything, and computing the square of that expectation doesn't change anything. So we have just one expectation. This quantity goes here without any changes. It's the same. Yet the same is true about this expectation, or the mean. The expectation of the mean is just the mean itself. So those quantities are the same. but the expectation of parameter squared and expectation of the parameter and the estimate of the parameter are still there. So what happens next is we observe that this expectation times that expectation is nothing but the expectation of our parameter estimate squared, and their difference will be precisely that expression. So this is our variance. Nice. What we see here is decomposition of the mean squared error into bias squared and the variance. So we can minimize the bias. Of course, when we minimize the bias, we minimize the variance simultaneously. Or do we? Let's see. Now, if data is all we have, this is as we thought about, or as we started with computational learning theory, right? In the Bayesian world, with the Bayesian approach, we have distributions of the data, or at least assumptions about the distribution. If we know the distributions exactly, then we can compute estimators exactly, or we can compute our classifiers, decision boundaries exactly. But if the data that we collected is all we have, then how do we know if we're doing well in terms of training a classifier? And also, if we have few hypotheses, we have few classifiers or few models, how do we know which model is better? So traditionally, to answer those questions, and having in mind that our goal is generalization, we don't simply want a classifier that we're working with to perform well on the data that we have at hand. We want the same classifier work well in practice, in the wild. We want to be able to deploy our medical scanning device, or we want to be able to put our loan credibility application such that new users, new people who come to the hospitals, new patients, are classified as correctly as our training data. But all we have is the data as we started. And how do we know that what we're training, the classifier we're training, is doing well? And one way to know that is to split our data into few parts. Usually it's 3 parts. Sometimes people start with just 2. If you only have one model that you're training, and this model is parametric, but you don't have any alternative models that you think will work well, then you split your data into train and test. You train your model on the training data, and you test the performance of the model on the test data correspondingly. But that is still not ideal, because, and I wonder, because well, assume that your model has hyperparameters. How do you decide which hyperparameters to use? Like, for example, k-means clustering, right? You want, well, although it's unsupervised learning algorithm, but you want to set the best optimal k. Or if you think about, Well, think about your naive Bayes example in your homework. If you want to select the width of the kernel such that the width of the kernel is optimal and the performance of the classifier is optimal, you don't want to use your train data for width selection because you're kind of being over optimistic. You will be over optimistic because you're optimizing your kernel width on the data you're training. So it's technically it's overfitting. Of course, you can always do that and find the best performance because you're simultaneously optimizing kernel width and the accuracy. But you can't do that on the test data either, because then it's double dipping as opposed to overfitting. So double dipping means is you're using your test data for your training. So for example, you could train in order to optimize the performance of the model, and then you can check and test how the model is doing, and based on that, on the test data, and based on that you can decide what hyperparameters value to set, as it was the case in your naive Bayes classifier. Since we can't use neither train nor test for hyperparameter setting, people usually go with this third subdivision, validation. So basically what the test set usually is also called is a holdout test. The model, or you as the experimenter, never see the holdout part. You only see the train and validation test. So you optimize your hyperparameters on the validation test set, and you train your model on the train set. Okay. Let's see if we have the split, what we can do with it. This is from Hastin, Tipshire, and Friedman book, Elements of Statistical Learning, the figure. So model complexity is number of free parameters in the model, the number of parameters that you're training. For example, if you have a polynomial of degree k, what we have here, your model complexity is this k. And so on till some coefficient, I don't know. That is your model complexity, and the number of parameters basically in your which are those coefficients for the polynomial case, but it could be number of parameters in your support vector machine, number of parameters in your other classifier, neural network, or whatever you chose to train. And we see that the higher is model complexity, that is, the larger is the model, the lower we can get the training error, that blue line here, which by contrast I'm underlying with the red color. Well, anyways, at the same time, that line is the test error, and as you see, another thing is depending on the data subset, initially those little thin lines are different data subset that you chose to train, or different split of your data into train and test. initially when you have just few parameters in the model, you have low variance in your test, but then you have high bias, that is high error. But once you're training, once you continue to train, you have lower bias, your error goes down, but you have high variance. And so high bias and low variance together, they form your error, right? Your error is high. Then at some point your bias is lowest, but your variance becomes starts to grow. I will show this on the next slide. Look at this. So if we look at this animation in the corner, then you can see that when your polynomial is of low degree, a line, then the fit is obviously wrong, but your variance is low, and then your variability becomes to grow like those wiggles, but your bias is low because you're now going through each of the points. So the line goes through each of the points. That means you get a perfect fit, or we call it overfitting. So if we look at this traditional diagram or classical diagram, algorithm complexity is basically the number of parameters in your model. Let's stick with the same family of algorithms. And number of parameters could be, say, number of layers that determines number of weights, and those weights in a feed-forward neural network are your parameters. So this is a deeper or wider or otherwise more complex neural network. The total error this. The true parameters and the estimated parameters. That's the red line. That the total error performs, and this is the test error or generalization error. That we're interested in. And generalization error goes down, so decreases with algorithm complexity. So when we're here, this regime is called underfitting. And underfitting, basically we are unable to capture the complexity, or our model is unable to capture the complexity of the data. Say in the animation there, if our data is truly nonlinear and we're trying to fit a line to it, yeah, apologies for like wiggly line there. But if we're trying to fit a line to a polynomial data, we're clearly underfitting. So if we're fitting second degree polynomial, we're probably somewhere here in the optimal regime. But then once we'll start going higher and higher and so on, we will be over here. Yes, our error will be the lowest, but our variance will be, our error, meaning our bias, will be the lowest, but our variance will be the highest. As you see here, with time, bias decreases, but as algorithm complexity grows, our variance increases. This is true in multiple ways. In order to avoid this part, we spoke about inductive bias, introducing some regularization to our models instead, to avoid or to prevent the model to simply memorizing everything, or to punish the models in the beginning of the course, if you remember, with our example with the square, where we have tasty bias and not so much for feature 1 and feature 2, and not so tasty bias. We could just remember all of that, and then all, like each of the point, and deductive bias is a way, as you remember, to avoid that memorization, because again, the whole point of our field of machine learning is to generalize beyond the training data. So that's about training one single model. What if we want to choose between a few different models or classifiers of different kind? Which one is better? This choice, or the problem of choice, is called model selection problem, and we want to select a model that will generalize best, right? We want to build a guess or an estimate of how well our model will perform on the future unseen data. And again, we look at the mean squared error. Let's look at the mean squared error between our estimate of generalization performance, this little g, that depends on the parameters on the model and the data, and the true ultimate generalization performance of that model that only depends on the parameters. Basically, this large G is performance on all possible data that we will ever see of that kind, right? And D is the data that we have, our data set that we have for training and for testing and for everything else. So imagine we found a model that has very low bias. It's basically an unbiased estimator. And if we look at here, you'll see that that's what basically is happening. That our G is our well, again, test error is our generalization error, right? Our G is our estimate of the generalization error, or else what is our estimate of generalization error is how well our model performs on some holdout data set, or some validation data set rather, which is d sub I here. And as you see, here, the error between the expected error of our estimate of the generalization, the little g, is the same as the actual test error, the green. But the variance is high. Look, if our d sub I was one of this, then we would be very optimistic. We would select a model that is minimal with respect to g, but we would be very wrong. If we would be unlucky and get this data set or subset, then we would be still very, very wrong, even more than before. And yet, according to our criterion, we would have selected the model that is best right now, and our model is low bias and high variance. Well, turns out low bias model low bias and low variance is good, of course, but low bias versus or unbiased even estimator and high variance is not good, because we can get unlucky, and most of the time we are unlucky. Look at the spread of this blue vertical lines where they could end up with respect to true generalizing estimate of the parameters. Yet if we take low variance and biased, look here, it's not precisely the same, green and red, although they may look the same, but they're not. So this estimate is biased, but the variance is low, so we can't be extremely unlucky. We can be somewhat unlucky with this data set when we select, value closer to 1 rather than 2. But look at this, we could be 6 rather than 2. It's like twice more wrong, sort of. So when we're doing a model selection, it is important to be aware of those things, and we'll talk about in the next part of this lecture about what to use for model selection and how to avoid the problems I've just described. And again, just to bring those points home about bias-variance trade-off and our kernel density estimator, remember the bias is when our estimator is wrong, so we wanted to estimate this blue line, but we're way off. Right, now we are estimating on average the blue line, but our variance is high now, move slightly left, slightly right, and you get very different value. So that's all about classical approach to bias-variance trade-off and model complexity. It's been a while, sort of a dogma, a gold truth that avoid overfitting. Don't select a very complicated model, or don't select a high capacity model. Select a parsimonious model with fewer parameters, and regularize with sparsity. Remember, non-negative matrix factorization was regularized with non-negativity as a proxy for sparsity. Then we can regularize with sparsity, L1 norm, again another proxy directly, or LP norm, L0 norm we can't optimize, is hard. Well, anyways, try to push the tradition or common sense, and actually truth is that we do want to keep our models somewhere here so we don't start overfitting. So what people in this paper, Misha Belkin and others, co-authors, they found that especially, actually with the neural networks, with large complex model with lots of parameters, you do see the classical bias-variance trade-off when you have underfitting and overfitting. Again, notice the dashed line in both of those figures is the training error. Your training error keeps going down, and if you were watching your validation set or you were watching your test set, you will observe that if you use more complex model with more parameters, your test error starts growing. So, okay, you're already seeing my error is growing. I don't want to use, I probably want to use more parsimonious model. But if you persistent and you want to avoid confirmation bias, you keep increasing the number of parameters. Well, Belkin and co-authors knew that surprisingly very large models perform really well. What they observed with this, and you can observe with them together in this bias-variance trade-off figure, that at some point your model becomes over-parameterized, and then the test error starts going down again. So look, you keep training, or you keep increasing the complexity of your model, and it's not there is not time here, it's capacity of the model. So you keep selecting a more complex model, and the model of course can fit your data, the training data, better and better with increased accuracy. It's not surprised. But after some interpolation threshold, after some point, surprisingly more complex models, which are called over-parameterized models, when you have way more parameters that are needed to just remember everything in your data set, but yet still generalization improves. Your test error goes down, and it's, as this figure shows, lower than the optimally achievable test error, generalization error with the classical approach. So that's it for now.